I actually think problem 1 from the 2004 E&M exam is fairly complicated. There's a lot going on in it. I would go for the maximum number of points at the very beginning of the problem, and then I would leave the rest of it alone. We have a linear charge density going into and out of the board, positive lambda. I know, I'm sorry, my handwriting sucks on this one. We surround it with a conductor. That's the key. Okay, first is sketch the electric field lines, if any, in regions 1, 2, and 3. Inside this interior region, we're going to have the electric field lines pointing outward. Since we're a little closer to the conductor on this side, those electric field lines are going to kind of push away from each other. These electric field lines are going to come straight out. The important piece to remember is that inside the conductor, there's no electric field. So no electric field lines inside that conductor. Excuse me. Outside the conductor, electric field lines continue to radiate outward. For putting the induced charge from the second part of part A, you should remember that since there's no electric field inside the conductor, if you used Gauss's law and put a Gaussian surface inside the conductor, there shouldn't be an electric field, so that means that somehow Q enclosed must equal 0. That means that negative charge is induced on the inner surface, and to keep the conductor at 0 charge, there must be a positive charge induced on the outer surface. So inner surface has negative charge, outer surface has positive charge. Next part, part B. List the points A, B, C, D, and E from highest potential to lowest potential. Should be obvious that the highest potential is going to be at D because that's the closest to the linear charge density. Then we would go to C as we get further out. Since B and E are inside of the conductor, and the conductor is by definition an equipotential, there's no electric field, but there is a solid potential. Every point on that conductor has to have the same potential. B and E need to have the same potential. Then A is outside the conductor, so that needs to have the lowest potential. Dramatic pause for this part. This is probably about as far as I would go with this problem before skipping it. So I would have gotten 3 points for the first part, 2 points for the induced charge, and then I would have gotten 4 points for the potentials. So I can do math. 3, 2, and 4. I would have gotten 9 points in this problem before I got into any of the math. Pause here. Okay, now the awful stuff. They want us to use Gauss's law to figure out the electric field inside of the 3 regions, but we've now replaced the conductor with some kind of material that has a volume charge density. This gets really, really bad, okay? We're going to rely on Gauss's law. E dot dA, integrate over a solid surface, is equal to Q over epsilon naught. We first need to figure out the electric field for the linear charge density. So I'm going to use Q is equal to lambda times L. L representing the length of our Gaussian surface. I'm going to use some kind of cylinder here. The area of a cylinder is 2 pi RL. That's what I'm replacing right here. Lambda L is going to be the charge over epsilon naught. Notice that the L's cancel out and we get the electric field from the linear charge density lambda over 2 pi epsilon naught R. Now I need to figure out the charge from the shell inside of the region. So this is the first area. That's for R less than R1. Once R becomes in between R1 and R2, I've got to figure out how much charge I'm getting from the volume charge density. So that means multiplying the volume charge density by the volume of the cylinder. But it's going to be the difference in the 2 volumes. So the total volume, how big that surface is going to be, it's not going out past the volume charge density minus that inner volume caused by the inner radius. Then we're going to use the electric field for that shell is going to be 2 pi RL. So once again, same Gaussian surface here, Q of the shell over epsilon naught. If you combine these 2 terms, you're going to get rho over 2 epsilon naught R, the difference in those radii, R squared minus R1 squared from this right here. Remember, we're inside of that volume charge density, so we don't have the total charge. We have the difference between how much we have from that volume charge density that we're going to use on Gauss's law minus that inner radius term. We combine the linear with the electric field from the shell, and we get our total right here. Now, as we move past, it's not enough to just say, oh, we're going to have pi r2 squared L, because that inner region is gone. That inner region is hollow. So we still have to take the difference in there to get the total charge on the shell, even when R2 is, or when R is bigger than R2. So the exact same thing happens. We get the exact same result. The only difference is now you're going to have R2 squared minus R1 instead of R squared minus R1. So that electric field becomes fixed for these two R terms down in the denominator. Now keep in mind that on that part C, that last part only gets you 2 points. All of part C only gets you 4 points. So I wouldn't really lose too much sleep over this. Excuse me, all of part C gives you 6 points. This, which I think is completely understandable, gets you 2 points. So all of the work before you started screwing around with that volume charge density, you got 11 out of 15. 11 out of 15 is well on your way toward a 5 on the AP exam. So don't get too lost in the weeds in here. Read through the solution, but don't stress too much on that if you have a hard time seeing it. But you have to take the difference in those volume charge densities, and that's the hard part of the problem.